All right, so welcome to this final session of the conference. It's a pleasure to introduce today's morning speaker, a Lichnerowitz Prize winner, Álvaro del Pino from University of Utrecht, actually also from Madrid. And he will speak about Haefliger structures and wrinkling.
Thanks a lot, Eckhart. Oh, this is really loud. All right. So does this work? Oh, yeah. No. OK, so yeah, I was telling Eckhart right now that I thought the title had been a terrible choice, because if you don't know what these things mean, this is completely nonsense, right? A better title somehow is Foliations with Transverse Geometry. That's what I'm going to talk about. And I mean, in some sense, it ties to other things you've seen this week, right? Yanis, for instance, was talking about yesterday about foliations with a transverse symplectic geometry. And he was doing analysis somehow. And I'm going to be doing some sort of topology. OK. All right. So, oh yeah, and the important thing is that this is joint work with Anna Fokma, who is right there. She's doing her PhD in Utrecht. And with Laurent Toussaint, he's a postdoc now in Amsterdam. I think many of you know him. This week, he couldn't come. So, OK. All right. Right, so what I want to do, I mean, maybe foliations with transverse geometry need no introduction because you all love them, but I want to do like a little baby example that I think it's pretty cute and it kind of motivates a bit the questions that I like, maybe. All right, so what is the baby example? So I fix a manifold M, and I'm going to be looking at functions on M. And I'm going to ask myself, can I classify the functions on M? And what does this mean? Well, it depends what I mean by classifying. Right, so first of all, I could say, well, I want to classify them up to homotopy. And I would just say, well, Symphony M is a topological vector space, say with the weak Whitney topology or something like this. And because it's a vector space, it's convex. So it's contractible. So everything is homotopic. So this is the end, right? We've solved our question. That was a baby question. Now, OK, maybe this is what you do as a topology remark. But if you like differential geometry, maybe you would say, well, I'm interested more like in the moduli space of functions. And you would say, I want to study them up to diffeomorphism or isotopy. And I don't want to talk about this at all, because this is not the purpose of the talk. But let me just say that, I mean, whereas the first question is kind of extremely flexible, as we said, everything is homotopic, not everything is diffeomorphic. In fact, there's like a big body of literature, apparently, in this problem. For instance, you can find papers of Arnold talking about this, and you have like something called rape graphs. There are some sort of combinatorial descriptions of like these diffeomorphism classes. So okay, if you are bored, you can Google rape graph, and it's kind of cute. But yes, this is not the point. What is the point? The point is that I want to talk about something else, and I want foliations to come in. So I want to talk about a third equivalence relation called concordance. So I want to say that two functions are concordant if they are homotopic. So to spell this out, this is that a function should exist on the cylinder going from one function to the other, right? This is just a homotopy. But I also want to have a foliation in the cylinder. This is a foliation by lines that should be transverse to the boundary. I will show you a picture in a second. So okay. And these two data are compatible in the sense that the function should be constant along the leaves of F. So okay, it's a basic function. It's a function in the leaf space. Okay? Okay, so this is what concordance is. It's an equivalence relation. And well, the question is, what is functions up to concordance? OK, so this is the baby question. And to make it even more baby, I'm going to specialize to the case of S1, because here you can work it out fully. And the point somehow is that you can work it out fully, because in this case, you know what all the foliations in the cylinder are. And this is kind of quite nice. I learned this from the book by Hirsch and Hector on foliations, which if you haven't checked out, it's pretty cute. I mean, it's a nice book. I don't know. It's just very readable. So let me talk about foliations in the cylinder. So the easiest foliation you can come up with is what we call a suspension. So you take a diffeomorphism phi isotopic to the identity. So this is just, in this case, it's just orientation preserving. Because it's isotopic to the identity, I fix an isotopy. And now I start at a point x, and I just follow this isotopy, right, until the endpoint. So x will be mapped to, I mean, as I follow its leaf, it will reach phi of x in the other side. So this we call the suspension of phi. And now there's a statement that says that every foliation in the cylinder transverse to the boundary that has no circular leaf is diffeomorphic to this one, or yeah, one of these. Diffeomorphic relative boundary. OK, so let me now show you the other ones, the ones that have circular leaves. So this has a circular leaf, right? It has a single one in the middle. All the other leaves spiral towards it. maybe let me say, in the previous example, right, the leaf space was just S1. Now the leaf space is a bit more exotic, right? We have an S1 worth of leaves coming from this side, an S1 worth of leaves coming from this side, and all of them kind of spiral towards the central leaf. In particular, the closure of this green central leaf is everything, right? This is a bit ugly topology. But the circles by themselves are nice, right? The circles by themselves are just a good old topological circle. Okay, so this is an example. I could have made some variations of this. For instance, I have some choice on how aggressive the spiraling is. I have some choice on whether I want to spiral up or down, but okay. Okay, second example would be, okay, now I thicken this central leaf to an interval worth of leaves. And now again, the orbit space is kind of, well, it's a bit similar, right? So we have the two boundary circles of leaves. We have this interval worth, and this right-hand side circle is accumulating against the rightmost closed leaf, and no, the leftmost is accumulating against the leftmost point, and the right circle is accumulating against the rightmost point. Okay. And for instance, here a little variation you can do, right, is that because now I have like an interval worth of circles, right? So these are fully single leaves without holonomy. I could replace the holonomy by some non-trivial diffeomorphism of the interval. If I want, that would kill some of the leaves. It would make them not closed and so on. But okay. Okay, and last example, let's move on from this. For instance, instead I could have maybe two circular leaves and I have a rape component between them. Okay, and here's its leaf space. What is the point? Well, the point now is that I've told you there's two situations, right? One of them is the suspension situation. Then there's at least one circular leaf situation. In fact, what I've showed you is kind of enough to understand all the foliations, because all of them will be formed essentially by things that look like this. You start concatenating copies of these various models, and you'll come up with everything. And what is the point? The point is with this, now we know how to answer the question. So the question was, what are functions up to concordance? And there's two situations, right? So maybe the concordance has no circular leaves. Then this just means that the function that I have on the left must be a reparameterization of the function on the right, right? So they represent the same element in the modular space. Okay, this is one situation. The other situation is if a concordance exists that contains a circular leaf, then both functions have to be constant. And why is this? Because what happens, I mean, you can see it easily in the leaf space, right? I mean, this blue thing is in the closure of this point. So the values in the blue circle have to all agree with the green point in the left. And similarly, all the values on this rightmost circle, they have to agree with the value at this point. Okay, so maybe the point to be made is that functions, they don't like to be crushed against things. And many geometries won't like this. They won't like to be kind of pushed towards a leaf aggressively. Okay. That's a comment. And what is the point? Now you can observe that if I have a constant here, what I can do is I can easily find a concordance between any other constant, right? Because I take the value of the constant here, it changes along the green interval, and then the other constant is at the other side. So what we've proven is that, okay, if you see a concordance of this type, then the functions have to be just constants, but they don't have to be the same constant. Okay, so what is the punchline? Let's wrap this example. The answer is that, well, we have a complete answer, right? So you just say functions up to concordance is basically one of the elements is the class of the constants, and all the other classes are isotopy classes of functions, of non-constant functions. Okay, what is the point of me rambling about this? Well, the point is that in this case, what we see is that the classification up to concordance is kind of quite similar to the one up to isotopy, and homotopy is just very different. Homotopy is just super flexible, right? Everything was just homotopic. Okay. Are we happy? Okay. Rui is happy. Very good. Okay, so now let me do, for contrast, a more interesting example, perhaps. So I want to look now at closed even-dimensional manifolds. And I'm going to write simp m for the space of symplectic structures on them. And okay, you know this. The classification up to homotopy in a fixed cohomology class is the same as a classification up to isotopy for symplectic structures in closed manifolds. This is just Moser stability. This says that, okay, these two things are, well, related in a non-trivial way in this case, or, yeah. And the point, of course, is that I guess the whole field of symplectic topology is about understanding these two things. How do you classify symplectic structures up to homotopy and isotopy? Well, it's a big question, right? But now, of course, I want to play the game I played before. I want to talk about this concordance idea. And okay, the good thing is that in Yanis's talk yesterday, he already explained this to you, right? So you already saw these objects. So I'm going to say, okay, and a foliation comes in now. So two symplectic structures are concordant if there's what? If there's a closed 2 form in the cylinder that has maximal rank, right? So it has rank 2n, but I mean, this is a not-dimensional manifold of dimension 2n plus 1, and it's closed, right? And what I want is that this form, it restricts to the boundary as the given symplectic forms. And as Yanis explained yesterday, I mean, you can call this a pre-symplectic structure of corank 1, right? Or you can call this a foliation of dimension 1 with transverse symplectic structure, right? So, I mean, this is kind of been the motto of how we got, I mean, we meaning Anna, Laurent, and I, to this problem. We ended up thinking about foliations with transverse structure as a natural generalization of just actual geometries in manifolds, and as something that gives you some interesting theory to classify structures on manifolds by themselves. So somehow this is the point. And okay, maybe let me make the point that, I mean, okay, as Yanis said, I mean, yeah, this is the key point to think about this is that we think about this as a foliation with transverse structure. That is really the point. Okay, so what is the answer to the question, what are symplectic structures up to concordance? Well, the answer was given by McDuff. Okay, wait. No, I'm getting confused with the two things. All right, so the answer was given by McDuff in the 80s, and she used convex integration. This is a H-principle argument, a scheme devised by Gromov. And what the theorem that she proved says is the following. It says, if I have two symplectic forms in the same manifold, then they are concordant if and only if they're cohomologous, and they are homotopic stably as maximal rank 2 forms. So for instance, we saw a similar phenomenon the other day in Jan Lee's talk, right? He said something like, if I have a B manifold and its divisor is coorientable, right, then the tangent, the B tangent bundle is stably isomorphic to the tangent bundle, right? So this is like two vector bundles. They are not the same, but they're isomorphic when you add one direction. And what we see here is kind of the same thing, right? So I'm talking about concordance, so I'm adding one direction. So I don't need to require that the two forms are homotopic as non-degenerate forms. I need to require that they are homotopic as non-degenerate forms upon stabilizing. Yeah. Okay, I don't know. I mean, you should really look at this theorem because this theorem is really amazing. I mean, this theorem should like blow your mind, in my opinion. Because, okay, I mean, in particular, okay, basically what we're saying, right, is that if two forms are what is called formally the same, so they represent the same almost symplectic thing and they have the same cohomology, in particular, they are related by concordance, which is definitely not true for homotopy and isotopy. That's kind of the central point in symplectic topology. And McDuff also proved the same thing for contact. So two contact structures that are formally isotopic, formally homotopic, they are in fact concordant through a foliation with transverse contact structure. And okay, let me tell you why this is completely insane. So you have two symplectic structures, and the whole point of symplectic topology is that even if they're formally the same, the fine symplectic features of them should be can be very different. And you will detect this with things like maybe holomorphic curves or things like this, or gauge theories or something. So okay, there's some fine symplectic topology happening, right? And however, you put a line field whose holonomy is symplectic, and this line field that we're constructing, that McDuff is constructing, must be so complicated, with such complicated dynamics, that every interesting feature on the right-hand side is being killed, and it doesn't appear on the other side. That is, I mean, it's super strange, right? You're constructing a holonomy that is symplectic, but everything is dying. And for instance, something I was talking to Robert the other day, and I told him, I would like to see actually what the dynamics do, because I don't understand. I mean, this argument is pure H-principle. You don't know what you've produced. But it would be very interesting to know what dynamics you have to put to kill things somehow. And let me make another comment. In the contact case, which is my favorite case, you can have a tight contact structure, a over-twisted contact structure, and some contact dynamics from one side to the other, and the over-twisted disk dies in the middle. It's pure, it's insane. All right, so okay, enough rambling. What is the punchline? The punchline is that somehow for contact and symplectic, unlike for the case of functions, concordance is much more flexible than homotopy. Yeah? Homotopy through symplectic forms. Okay, so what is the reason? We've seen two geometries, functions on one side, symplectic on the other side, and the behavior is quite different. What is sort of the moral of the story? The moral of the story is that somehow nature really likes contact and symplectic geometry, and that kind of maybe justifies why we are all here, right? Somehow there's a lot you can do with symplectic geometry, right? Because in some sense it has much better properties than your average random geometry. So for instance, let me give you a list. So, okay, for instance, contact and symplectic, they have a local model, but okay, many geometries do. This is maybe not the most special thing. Much more especially, they're globally stable, right? And closed manifold, so you have Gray and Moser stability. That is really, really rare. They have a ridiculous automorphism group, right? So symplectomorphisms and contactomorphisms, they are groups that in many ways they're like the diffeomorphism group. There's a lot of stuff, right? In the Riemannian case, you would have a finite dimensional A group, right? It's so large, in fact, that it's n-transitive. So this means that any configuration of endpoints, you can move to any other configuration of endpoints. This is a way of measuring how flexible this group is. And it satisfies what, okay, when you look at the Hamiltonian case, it satisfies what we call fragmentation. So this means that a Hamiltonian isotopy, you can write it as a composition of little Hamiltonian isotopies that are compactly supported. So you can sort of cut off in the automorphism group, which is very strange. In fact, I don't know if I know any other examples apart from this and diffeomorphism groups and maybe a handful of things. Okay. Okay, so this is kind of, okay, this is why they are so special, and this is why maybe all of us study these things. Let me just jump through this comment because, okay. So the point is, okay, maybe all of us are in this room because, well, in some sense, our area came from kind of symplectic geometry, right? I guess, in a way. But this is not what I want to do. Somehow, I don't want to work with the geometries that we all like. I want to talk about the other ones that nobody likes, maybe, right? So what I want to focus on is sort of trying to show somehow that when we study concordance for an average geometry, the situation will be much closer to the function case than to the symplectic or contact case. And I mean, this was a bit kind of our point a bit with this project. We wanted to understand just general geometries and see how they differ from these ones that are super nice. Okay, this is the philosophy. Are we happy? Okay. All right, so now I should actually tell you some proper math, I guess. So I should kind of maybe, I mean, I want to tell you what I mean by geometry, right? Because, for instance, Marius was using the word geometry, and it was not exactly what I'm saying, I think. I'm going to talk about what the transverse geometry in a foliation is. I will define what a Haefliger structure is, and so on. So, okay, let's just go through the things. All right, so to tell you what a geometry is in fact easier if I just kind of spell out what I like about symplectic structures, and then I tell you what are things that are kind of like that. So, okay, what are symplectic structures? So there are two forms, right? So there are sections of the second stereo power of the cotangent bundle. They are not arbitrary sections. They are sections that satisfy certain differential conditions, namely they are non-degenerate, right? This is a condition on omega itself, and they are closed, right? So this means this is a condition on the first differential. These conditions are maybe intrinsic or natural, you may call them, right? So they are not differential conditions that depend on a chart or a concrete representation of your manifold locally. These are things that when you change charts, the equations remain the same, right? And the reason, right, is that the run differential is sort of an intrinsic thing in a manifold, and the wedge is also intrinsic, right? So, okay, we have these kind of invariant PDE on manifolds. Okay, I'm getting confused again. Right? Additionally, they form a sheaf, right? I can talk about the symplectic structures in a subset of my manifold. And the way I want to think about it is that a sheaf is with values in topological spaces, right? So I'm thinking that as sections of a bundle, they have perhaps the weak Whitney topology or something like this, okay? Okay, so they form a sheaf. And of course, well, this sheaf is also invariant under diffeomorphisms, right? If I have two opens that are diffeomorphic, then the corresponding spaces of symplectic structures are homeomorphic. And you can say probably they are diffeomorphic if you put kind of some nice manifold structure on it, but okay. Okay, so these things we like. So what's a geometry? A geometry is a similar thing, kind of. So, okay, what I want is a bundle on my manifold. I'm going to call that X, and I want that this bundle is what we call natural, so it comes with an action of the diffeomorphism group. So you should think the tangent bundle, right? Whenever you act with a diffeomorphism in the base, you differentiate, you apply it to vectors, and that's an action on the tangent bundle. The cotangent bundle is the same, tensor bundles are the same. These are maybe your typical examples of natural bundles. Okay, then additionally on this bundle, I want to study sections of that bundle, but I want them to satisfy some intrinsically defined PDE, right? So what I'm saying is, okay, the section should satisfy some differential condition that is invariant under diffeomorphisms. Again, you should think things that involve wedges of forms, that involve differentials of forms, things that involve the Lie bracket of vector fields, things like this. Okay. Okay, and what this says, of course, is that then the sections that satisfy this constraint, they form a diff-invariant sheaf with values in topological spaces again. And okay, I keep saying like the manifold M, but in fact you should forget the manifold M, right? Because what I'm telling you, right, is that because these constraints are invariant under diffeomorphisms, this means that these constraints, they live in all manifolds at once. So in fact, the way to talk about these things rather is that you should think that this is a diff-invariant sheaf in all manifolds together. So it's a sheaf in the site of manifolds of dimension Q, where Q is the dimension I'm working on. Okay, yeah? So now we are all experts on what a geometry is. In fact, I mean, maybe let me say, I mean, in fact, this whole bundle description I could drop, and I could basically try to work with things that are just like this, with sheaves on man. And you can do that, but that would make maybe things more confusing. So I won't do that. Okay. So we know what a geometry is. Let's do transverse geometries. Okay, so, right. So the heuristic definition is that a transverse G geometry on a foliated manifold is a solution of this geometry, right? So one element of this sheaf in the leaf space. Okay, this is the moral definition. The way you actually implement it, I guess, is that you say, well, okay, I take my foliation, I fix a transversal. The transversal is an actual nice manifold. I put a solution of G there, and now I ask that it's invariant under holonomy. Yeah, this is maybe like your pedestrian way of doing it. Okay. And now what is the point? Maybe, right, so what we've done at this point is that, well, now we can talk about foliations with arbitrary transverse geometry of this kind, and now I can talk about concordances. And maybe let me observe that now I'm going to do something more general. So in the examples we saw in the beginning, we had two manifolds that didn't look very foliated, right? But they were foliated. They were foliated by points. And then I kind of put a foliated manifold in the middle to serve as a concordance. What I'm doing now is I'm going to say I have two manifolds. They have a foliation with transverse geometry. And I'm going to put a foliation with transverse geometry of the same corank in the manifold times interval. And this will be a concordance between them. Yeah. And so this is what it says. This is the equivalence relation that is kind of natural for foliations with transverse geometry. Okay. And now something that I want to do is kind of spell out the typical principal bundle description of these things, and I'll tell you what groupoids kind of come into this. Right, so what do I have? I have, as I said, I have a manifold with a foliation F and a transverse geometry sigma. Here it is. Now I take a foliation chart, and okay, this maps to Rn, right? And this is, well, it's foliated itself. Now I have, given this foliated chart, I can pick a submersion to its leaf space. I call this the composition of these two things pi I, right? So this is a local submersion into RQ, and the foliation locally looks like the fibers of the submersion. And okay, this would be enough to describe the foliation, right? But here I need the transverse structure, and the way you see it is that over the image of this chart, you'll see a solution of the geometry, right? You will see an element of the sheaf. Right, so this is what in Yanni's talk we saw, right? So kind of you would project to the leaf space, and then you see there an actual symplectic structure. No mystery here. So what is the way to phrase this? All right. Oh yeah. And okay. I mean, I've told you what I'm doing on a chart. I should tell you what we do on transitions of charts, right? And what is the point? I have two charts that overlap in the manifold. You map them to RQ submersively. Over every opening RQ, we have a solution. Now, the transition of the foliation itself will give you, well, a transition between the overlap of these two charts. But additionally, what I need is that the transition function, it should preserve the geometry, right? So these are not arbitrary diffeomorphisms. They are diffeomorphisms that preserve the geometric choice I have in the normal bundle. Well, transversely. Right. So, okay, maybe to spell it out. So what I'm saying is that a foliation with one of these transverse geometries is a two cocycle valued in a certain groupoid. What is this groupoid? Right. So that's, as we said, when we're on a chart, right, we're mapping to RQ. And over RQ, I'm picking a solution. So that means that where am I mapping? I'm mapping to the étal space of solutions over RQ. Right? So I have to just not map to RQ. I have to remember this important data, right? So okay, so here we have the base of our groupoid. It's the étal space of solutions of G on RQ. And now when I look at transitions, right, I see that the diffeomorphism group acts on this, but I don't look at arbitrary diffeos. but rather diffeos that preserve the geometry. So this means that I'm looking at the action of the groupoid of diffeomorphism germs of RQ as it acts on solutions. So this is, yeah, some action groupoid. And I mean, maybe note that the base of this groupoid is already, so everything is étal here. So sort of everything here is, in all the cases we look at, it's basically non-second countable, non-Hausdorff manifolds. But okay. Okay. Yes, okay. Please.
Hi. No, thinking in reducing the structure group, these kind of geometries that you are studying, are they characterized by the automorphism they have? Or
this kind of geometries? Right, so maybe I should make a point. Maybe this is the point we use the board. So the point is what? The point is the geometry as being G, right? It has basically, its automorphism group is a diffeomorphism group of the manifold or whatever, right? It's the full of diff. But that doesn't mean that an individual solution has any symmetries, right? So for instance, sympletic structures by themselves, they have many symmetries. But if I have a random geometry, even if the geometry as a whole is very symmetric, a solution may not be, right? Because many geometries don't have a local model. They have ridiculous moduli spaces of solution germs. So maybe, I don't know if this is a comment that would help, but for instance, maybe something to be said is that, for instance, like a typical example that maybe, that people like, well, in Marius's kind of school have studied a lot, right, is that you would, for instance, look at, right, like things like G structures, right, or so. And here you have a local model, right, because symplectic geometry has a local model, and then you look at the groupoid of kind of automorphisms of this model, right? And my claim is that what we're producing is not the same, but in the symplectic case, for instance, but it's Morita equivalent to it. You can sort of, when you have a local model, you can mod out many of the things, and you will pass to this picture. Is that, maybe that's where it was going? I don't know. Well, we can, okay, you should complain more, Matthias, later, and then we can discuss. Okay, are we happy? Okay, right, so we have this groupoid. I think this doesn't work. Perdonad. Creo que, yeah. No. Okay. Well, maybe, oh, there we go. Oh, right. Right. So what am I saying? So we've said out of our data, we have produced a Tuco cycle. This is just sort of a way of presenting our data. Of course, I could have produced many other equivalent Tuco cycles. The intrinsic way to say what I'm saying is that what we are producing is so okay, I call this groupoid gamma G, and we are producing a principal gamma G bundle. Yeah. And okay, maybe to say it explicitly, what is this? So at a point in M, right, the elements of P, what they do is they are all the possible submersions into RQ. Well, not into RQ, but rather into the étal space, such that the transverse structure upstairs pulls back the universal solution in this étal space. Right? After all, this is the space of all solutions, so at every point, at every germ, which is a germ of solution, you have a solution that you pull back. Okay, this is a weird thing, but okay, there's a principal bundle going on here. Okay. And maybe let me make a very quick comment. So something that you want to do in these things, for instance, when you're studying standard foliations with no transversal structure, you would say things like, okay, I have the groupoid gamma Q that classifies, let's say, foliations. And now what you could do, right, is you could associate, given a foliation, you can take its normal bundle. This is just a vector bundle. So this would say that gamma Q maps to the Lie group GL, right? So the structure group of the normal bundle. And what we have in this case is a generalization of this. So we have another groupoid. It doesn't matter very much what it is right now because, okay, we won't talk about it much. But the point is that basically what does this other groupoid encode? Well, it encodes what the normal bundle is of the foliation. And basically in every normal slice, it remembers what is the germ of solution. But it doesn't remember how they glue together to form a foliation. Somehow, at every point you have a germ of solution, but they vary just in a smooth, nice way. So for instance, you can think that maybe in the symplectic case, this would just be the symplectic group, right? You would not remember just the normal bundle. You would remember the normal bundle as a symplectic vector bundle. It remembers also part of the geometry transversely. Okay. Bisections are local solutions. Yeah, sure. Okay, let me think about that, and then I get back to you. Well, but I mean, okay, you should, you should think really that this is some sort of like just a Lie group acting on the possible solutions, right, at the origin or something like this. Yeah. Mm-hmm. Yeah, exactly. The way I would imagine it is that, what I'm remembering is the normal bundle, right? And in every fiber of this normal bundle, I'm remembering the germ of the metrics. I'm remembering not just a scalar product or so, but I'm really remembering like all the way up to germs. But they just vary smoothly, right? I don't have to remember how they paste together. Eckhart, how am I doing time-wise? Okay. Oh, that's not good. That's really bad. Okay, so what is the point? As I told you, the point of this talk is that we want to do foliations with transverse geometry and study them topologically. And what was Haefliger's amazing insight is that you can generalize foliations a bit and obtain a class of geometries, let's say, or a class of structures that is flexible enough to be studied nicely by homotopy theory. And this is what I want to tell you, and this is one of the main tools we will use. So this is what Haefliger structures are, and let me give you a motivating picture. So let's say I have a manifold with a transverse geometry, right? And here I have just a vector bundle on top. And the way you should think about this is that it's a submersion, right? But it's a submersion where the total space is homotopy equivalent to the little space. And if I'm a homotopy theorist, I'm sort of just blind to these things, right? I would say, well, E and M are homotopy equivalent by this map. They're the same thing. I'm happy to pass from M to E, from E to M. And what Haefliger said is, well, in fact, you're also happy, if you're a foliation theorist, you're also very happy to just pass from M to E and from E to M. Because the point is that because this is a submersion, I can pull back both the foliation and the transverse structure. And now I will get something whose leaf spaces are essentially, well, literally the same. Yeah. So as a foliation person, this game is fine. And once you've accepted this, then you can also accept this. I can say, well, let's say I have a manifold. Let's say my manifold is just a point, and I want to make sense of what it means to put a codimension 1 foliation on a point. Well, apparently I'm perfectly allowed to take M and thicken it to this plane, for instance. And now I foliate the plane by lines. Well, now this is, if M is E and E is M, this is a codimension 1 foliation on M. Morally speaking, as a homotopy theorist, I'm sort of, just blind to this dimension question, right? Okay, so this is a bit the philosophy. And now let me tell you a bit what Haefliger did. So this is in two really nice papers by Haefliger. They're basically the French and the English version of the same thing, you could say. But they're really nice papers. And the point that he made is the following. So the issue about foliations and about many other geometries, right, is that you cannot pull back a geometry and obtain a geometry. Right? In general, for an arbitrary map, you can do it, let's say, for submersions or things like this quite often when you have some transversality, or depends, yeah? But what he observed is that, well, okay, there's a way of salvaging this if you're willing to go to a more general geometry. So there's this geometry called Haefliger structures, and you can always pull them back. And they are a slight generalization of foliations. And what is the idea? The idea is the following. I have a foliated manifold with transverse structures, say, and I have an arbitrary map. And what I want to do is pull back this data by little f. Now, what you can do is you can write little f as the composition of the graph of little f, followed by the projection onto the m factor, right? And okay, pi is great because pi is a submersion. The problem is the graph itself. Yeah. Now, of course, I don't need really n times m, right? Because in some sense, if I just care about f, well, I only care about the graph of f. So I may as well forget what happens far away and just focus on a germ or neighborhood around this. So, okay, this is where the action is happening. And now, as I told you, I'm happy to just pass from a manifold to a vector bundle on top and pretend nothing has happened. So here it is. Here is the pullback, right? The pullback is I took n, I have this thickening of n, and in this thickening of n, there's an actual foliation with an actual transverse structure that I just pull back by the submersion pi. And this is literally the same picture, except that I took the graph and flattened it out to make it more look like n. Yeah. And just to say, you see now this, for instance, this foliation when you would actually get a foliation on n, it comes transversely to n. But exactly the points where you would have a problem due to lack of transversality, they will turn into these things. Right? They will be actual singularities of the foliation with the base. Okay. So yeah, this is what a Haefliger structure. We think of it as a singular foliation together with a desingularization. And maybe the warning is that you learned maybe last week in the mini course what a singular foliation is, and this is not that. These are kind of different notions of singular foliation. One can try to say things and relate them, but that's not the purpose of today. Okay, so just be warned. Okay. So, okay, let's put a proper definition. So a Haefliger structure, there's several ways of talking about Haefliger structures. In a second, they will be principal bundles. But this is kind of the geometric description or topological description. A Haefliger structure with a transverse G geometry is a triple of, well, E is a bundle over M, which is the thickening. F is a foliation on the thickening. And sigma is a solution, a transverse geometry to the foliation. And here there's this key property which says that the foliation should be transverse to the fibers. You may check that this is exactly what happens here, and let me explain to you why that is kind of the crucial property. So what we're saying is we have here M, and here we have this thickening, and with this property, this means that the normal bundle of F is vertical. It lives along the thickening. And this is amazing, because what you're saying is if I have any map, and I pull back this bundle, I'm pulling back the normal bundle with me. And if I pull back the normal bundle, the normal bundle is literally what is the part transverse to the foliation, which means that the induced map upstairs, it is transverse to the foliation. So you're kind of adding in the directions you need to be mapping transversely. And now I can pull back the two pieces of data. So this is the proof. This is what Haefliger observed, that once you've set up this theory, you can start pulling back in a nice way. Okay. Yes, okay, that's the next slide. So let me just maybe show the whole thing at once. So, right, and the proof is very easy, right? So if I have a foliation, if I have a Haefliger structure in this sense, it's a foliation on E. So it has a cocycle description as a foliation with transverse structure. Now, as a cocycle, the cocycle can be restricted to M. That is certainly not a problem. And then I get this gamma G bundle over M. But the point now is that, before, right, what we had is, when we have an actual foliation, you submerge into RQ and you're pulling back the solution. And this meant that the moment map of the principal bundle was submersive. Somehow mu basically reflects the properties of these charts. But when I'm doing this, right, when I'm restricting the cocycle to M, well, M is not transverse to things, right? M is not given by a submersion. If it was given by a submersion, I would have a foliation. So this moment map, I'm allowing it here to be whatever. It's any map. And a sentence that I think is helpful to remember is that, a foliation is to a submersion what a Haefliger structure is to a random map. That is exactly the philosophy you should keep in mind. Okay. Matthias, that's an answer, right, I guess? Okay. So yeah, this was the point. Okay, so let me tell you what the classic, some very nice classic theorems. Right, so the paper that kickstarted this area, this is what Haefliger observes right after doing this construction we just saw, is he says, well, okay, now that I have Haefliger structures, I can talk about concordances between them. So this is, again, I add one dimension, and I want a Haefliger structure in the middle that restricts. Okay, I'm going to write Haefliger GM for Haefliger structures on M with that geometry. And the beautiful thing is about this is that once you've set up this groupoid story, you get the classifying space for free, right? This is the nerf. And what he proved, right, is that, well, Haefliger structures up to concordance through Haefliger structures are in one-to-one correspondence with homotopy classes of maps into classifying space. Okay? And now this is the point, right? This is why we're doing homotopy theory, right? Once you've passed to, I want to study maps into something up to homotopy, well, this is homotopy theory, yeah? And you can study it as such. Okay, so this is amazing. Okay, but the question at this point is that you may say, well, okay, we came up with this new more general notion. We proved that this is very homotopy theoretical, but why is this good, right? And this is here's the result. This is in Haefliger's original papers. So Haefliger did it for a manifold that is open, M, and Thurston did it for a manifold that is closed. And what they proved is that, in fact, the space of Haefliger structures up to concordance is the same as the space of foliations up to concordance. There's no geometry here. This is just foliations and Haefliger structures naked. So in particular, what this says is if I have a Haefliger structure, I can always regularize it. So I can homotope it in some way to make it into an actual foliation. I can remove these singularities. And if I have a concordance of Haefliger structures between two foliations, I can make this a concordance of foliations. Okay? So this is kind of quite amazing because now we are studying, now we can really study foliations with homotopy theory. Okay, and now at this point, the game is to try to understand what is the homotopy type of the classifying space. Right? That's what we've done. And let me give you some results. So for instance, Thurston proved that some things were known, but I didn't remember who did this before, so okay. So the general case was done by Thurston. So any hyperplane field in a manifold is homotopic to a foliation. Okay, this is a normal person statement. A fancy statement is this. A fancy statement says, I have the classifying space of the germs of diffeomorphisms in R, right? I have a rank 1 foliation, so its normal bundle is one-dimensional. And what we are saying is that this is homotopy equivalent to the classifying space of the normal bundle itself. And I'm decorating it with these things that says kind of monomorphism or something because, BGL1, it just classifies the normal bundle as a bundle. But I should remember that the normal bundle has to be inside the tangent bundle, right? So that's what mon means. Okay, let me give you another statement. Haefliger, Mather, and Thurston, increasingly kind of better results in some sense. They prove that any two-plane field is homotopic to a foliation. And the classifying spaces statement is this. So let's unravel what this is. This says, the map into the classifying space of the normal bundle is Q plus 2 connected. So let's play the game. I take a Q plus 2 manifold. I look at foliations in it of codimension Q. So this is, right, foliations of dimension 2, so planes. And this says that they are classified indeed by the map into a classifying space. So yeah, so this is just a fancy way of saying what this statement. And okay, there's a famous theorem by Thurston that says that this classifying map is at most 2Q plus 1 connected. And this is based on the Godbillon-Bay invariant, but I don't really know the proof, to be honest. But there's a conjecture by Haefliger and Thurston that this is kind of sharp. So the expectation is that this is 2Q connected. And this is maybe one of the most important open questions in foliation theory. So there's that. Okay, so now let's do transverse geometries. So basically, McDuff proved a lot in the 80s. So what she said is, using convex integration, line fields with a transverse volume, this is somehow one of the simplest geometries you can come up, are flexible. And there's an analog of this in classifying space, but okay. This says that if you have a line field that is transversely orientable, I can always homotope it to a line field that is actually has a transverse volume. Okay, she proved the same for symplectic structures. We saw that already. Line fields with a transverse symplectic geometry are easy to construct. That was kind of the point, the example we saw before. Again, there's a statement for classifying space. And she proved that also the same thing for contact structures. So line fields with transverse contact structure are also flexible. But in fact, there's been activity in the last 2 years or so. So Sam Nariman, he proved that you can upgrade this by 1. So you can talk about also plane fields. And let me say a caveat. So McDuff constructs actual line fields with transverse contact structure. But Nariman doesn't. Nariman, what he constructs are Haefliger structures of dimension 2 with transverse contact structure. But he's not, he's in principle not able to regularize to an actual plane field with contact structure. And this is maybe a point to be made. So we have this regularization scheme by Thurston and Haefliger that says that every Haefliger structure, just naked, I can homotope it to an actual foliation. But when you put a transverse geometry, your regularization tricks don't work. So, well, we don't know if they work. So this is an open question. Okay. Well, certainly cannot work in general in any case.
Would you know?
No. Basically, I don't know any trivial. No. Basically, right, it's also the point about H principle, right? If you knew how to do this, you would be able to construct actually quite a lot of geometries. Okay, so maybe I'm lying to you. Maybe I know how to do it for rank Q foliations in Q-dimensional manifolds for geometries that satisfy the H principle, right? Which is a kind of weird way of stating the H principle, I guess, but it. Sure. Yeah, maybe I should say, well, yeah, that's correct. Yeah, thanks, Ree. That's a good comment. Okay, so I'm doing terrible on time, right?
Well, it's 10:45.
Okay, so yes, terrible. Okay, let me just state the theorems, and I will give you a flavor, and then we have questions, I guess. Okay. So what is the setup? The setup is that I have a geometry that is described by an open condition. So this would be an inequality of some kind. It should be diff invariant, and it should be for q-dimensional manifolds. And okay, here's a statement. Gromov proved this, that the classifying space in this case is always q-1 connected. But I mean, this is just, again, a weird way of stating the typical Gromov principle. Yeah? So every formal solution of the geometry in a manifold of dimension q, it cannot be homotoped in general to a solution over the whole manifold, but it can be homotoped to a solution over some manifold of positive codimension. And this is what this says, right? It says that over q-1 manifolds or lower, I'm fine. And basically what we kind of observed is that you can promote this to q-connected. And the point is that much like this is the fancy way of talking about holonomic approximation, in fact, basically our main observation is that this is the correct way of talking about wrinkling. Whatever that is, it's another H-principle technique, but this is kind of the Haefliger way of phrasing it, and in fact, it's kind of the way of phrasing it for every geometric structure. Okay, so this is what it says. Every formal solution over a manifold can be homotoped to a global solution, but it may be singular in this Haefliger sense. Okay, so I think I wanted to show you the proof very quickly. Maybe let's maybe rush a bit through it. So, okay. So I wanted to do the example of I want to construct, well, okay, let's just jump ahead. I will just show you, I will avoid these nice pictures. So let's just maybe give you the general argument and we move on. So what does this say? This says, okay, I'm talking about Q connectedness, so I'm talking about Q manifolds. It's talking about some relative homotopy group, so I'm really talking about the disk of dimension Q. And I'm saying that I'm looking at some relative homotopy group, so this is saying that along the boundary of this disk, I have an actual solution in the Haefliger sense. Okay? And now what you want to do is extend this Haefliger solution to the interior of the disk. And what do you do? Well, as a Haefliger structure naked with no geometry, you can just do it because of the smooth case. And then you can basically apply various H-principle things to make it work. And what is the point? Basically, the point is that you will be, even if you had no singularities of the foliation, you will be forced to introduce new singularities to be able to complete the argument. So this is what I was saying. You will always construct things that have singularities, right? And maybe let me give you the punchline a bit. This is how we started on this story. So the point is this. What is wrinkling? Wrinkling is some general philosophy by Eliashberg and Mishashev that says, I should be able, given a formal data, I should be able to construct a solution of that formal data with singularities. And all the instances in the literature of this are done like in an ad hoc manner. So basically, the first case was done by them about submersions, and you prove some statement where you say what a wrinkled submersion is, and that's some work. Then a very famous theorem that I think all of you maybe know is the folded sympletic structures of Anacanas. So she defined what's a folded sympletic structure. Well, it's a thing that looks like this. And you constructed with this wrinkling argument of constructing singular things. And then this was again used by Borman, Eliashberg, and Murphy in the contact case as one of the first steps in their H-principle for contact structures. What is the point of the talk, or the observation that kind of made us start this project, is the fact that all these statements are proven kind of with, you say, oh, it's something that looks like this singular solution. And what we kind of observe is that Haefliger structures are the right language for talking about wrinkling. That's maybe the punchline. So in some sense, we just observed that there's some nice language to talk about this for any relation. And then, the byproduct, of course, is, and then you can talk about classifying space, which will turn out to be useful in 1 second. Okay, and this relates to some previous work of Laurent to Saint-Anay in jet space, but okay, let me move on. Okay, theorem 2. Okay, this is terrible. I will run. So what is the point? The point is that the previous theorem is sharp. So what we want to prove, is the following. We want to prove that this classifying map is not Q+1 connected. So yeah, we want to prove that this classifying map is not Q+1 connected. So our previous result was sharp. And we would like to prove this for as many geometries as possible. And heuristically, what I want to say is that most geometries will be of this type. Kind of concordances will be very rigid for most geometries. However, what we have so far, I should have probably write in progress here, is that we have, we understand it very well for one geometry, namely immersions. And now basically the work is to try to do it, for instance, for Riemannian, that would be probably a good one, because kind of Riemannian structures don't have a local model. It's super wild, so it should work, but okay, we haven't done it. So this is the claim. And now maybe let me just show a picture, and then we wrap, and then you ask questions. So what is the point? What you should observe, and it's a very naive observation, is the following. If I have my manifold M, and I have the étale space of solutions, what is the étale space of solutions? Okay, maybe it's a weird object, but it's a manifold of the same dimension as M, right? That's just non-second-countable, non-Hausdorff. You should imagine that it's some sort of like super strange covering space of M. And all I'm saying, in some sense, is that if I have two sections, they will never be homotopic to each other unless they're literally the same, right? And this is kind of logical in a covering space. I cannot just jump a sheet with a homotopy. Of course, you may be worried that because this étale space is kind of ridiculously weird, for instance, you have this thing, right, where a function that is identically 0 is also, it merges with a function that is kind of positive and then 0 over the half line. You have this kind of branching phenomenon all over the place, right? It's a weird thing. But this basically presents no problems. And the funny thing, I think, is that how we prove it is we say we fix a germ. So this is a point in étale space. And now we pair homologically against it, or we do intersection pairing with a point. So the idea, right, is if you have some homotopy, even though you're in a weird manifold, you can apply transversality, and any homotopy, so this is parameterized by M times interval, it will cut the point in a one-dimensional object. And this means that if this germ is seen by this section, it must be seen by this section because, well, you cannot, right? One point is not coordinate to a 0 points. So this says, yeah, okay. So maybe let me tell you, to me, I find this very strange somehow that you're doing intersection theory in a weird manifold that is non-Hausdorff and massive and so on. But okay, so this is the statement in étale space, and what I'm saying is, what you have to do in the general case is, you don't have just étale space, you have the action of the diffeomorphism group. Right? So given a germ, that germ is not alone. It has many copies that are the copies of it by acting by a diffeomorphism germ. And what you're trying to say is, I want to pair homologically with many, many, many points. And the assumption that we need somehow is what we call being isolated. This point must not see copies of itself nearby. So this means that you don't have a local model. In fact, you don't have anything that looks remotely close to yourself. And in some sense, the claim would be that a generic geometry would satisfy this. But okay, that's work in progress. This is certainly true for immersions. That's an exercise maybe to think. But the proof basically concludes by saying, well, if I have something here, a solution, okay, the claim is, if I have two solutions of my geometry, in this case immersions on a manifold, and I try to find a concordance in the middle, what I can do is I can detect which of these, in which points the germ of the solution agrees with the marked germ, and then it will be the case, using transversality, that this germ must be seen in the other side. And if I have two solutions, all whose germs are the same, well, that's kind of the argument that tells you that, well, most things won't be like that. They won't be homotopic. Okay, so that is the end. Yeah, blah, blah. Yeah, so, okay, as I was saying, this is work in progress. We're looking at other geometries. We don't know how general this is. And let me maybe say, so maybe a question that I think is a bit interesting. Oh, sorry.
You have a few more meetings.
Oh, really?
Yeah, you don't really have.
Oh, I thought I was like at 50 already or something like this.
No.
Oh. Well, but I'm also done, in some sense, because I was rushing through. Interesting. Okay, well, then you can ask. Well, okay. Then let me maybe ask the questions properly, at least. So as I said, okay, there's some work to be understood about understanding other examples. In fact, now all of our arguments, right, for proving that we have like really big homotopy groups in this dimension Q+1, right, they should adapt quite more generally to higher homotopy groups, and then we would be talking not about finding concordances between solutions of our geometry, but finding concordances between foliations with transverse structure with that geometry. And I think that should work kind of the same, but we haven't thought about it really, but I think that's interesting. A question that I think is very intriguing somehow is that, our argument uses very strongly that you don't have a local model for the geometry. That's really crucial. However, on the other side, you have contact and symplectic, for which we know that the conclusions of the theorem don't hold, right? You get this extra connectivity. And those are geometries that have a local model, but in fact much more, as we said. And the question somehow is, if you have a geometry that has a local model, but it doesn't have all the other nice properties, I don't know where it lives in this story. Is it more similar to the concordances are rigid story, so you can find an obstruction in homotopy groups in the in dimension +1, or is it closer to contact? We don't know. So for instance, I mean, I don't know, maybe some of you know, I like this geometry called angle geometry. And angle geometry is, it has like some local model, which is nice. It has some automorphisms. So maybe one can try to say that you get extra connectivity in that case, but we just don't know. OK, then there's a funny question here somehow. So this is a funny question, so maybe let me, not maybe the question, but maybe the philosophy. So as I said before, this project kind of started, I mean, so a few years ago, Lorana and I got interested in this idea, right, of wrinkling, in constructing geometric structures with singularities. And what we did, we proved this last year, and this is still a bit ongoing, is that we observed that you can talk about singular solutions as some manifolds in jet space tangent to the canonical distribution in jet space. And we proved some flexibility result for such things. And now we have this thing about Haefliger structures, and the techniques are very different, and the language is very different. And the question is maybe, how are these things related? And in some sense, what we are doing right here is the étale germ version of what we were doing. You have this tower of jets, and at the top, you have germs. And in some sense, you could think that talking about things that are tangent to the Cartan distribution in jet spaces, it becomes being continuous for the étale topology upstairs. A way to say this is that sometimes we say that in J infinity, the Cartan distribution is involutive, and you may want to think that its integration is exactly this germ space, this étale space. That's a moral way of talking about it. And there's some question then that you can try to relate, indeed, kind of homotopy classes of maps tangent to the Cartan distribution, up to homotopy tangent to the Cartan distribution to actual homotopies in the étale space. I think that's kind of cute. There's some questions about this. And maybe just to close, I think something that I kind of find quite interesting these days is that, I mean, I wrote it a bit randomly, but maybe the question somehow, for instance, would be like, what is an interesting concordance theory for singular foliations? Definitely you don't want to allow all singular foliations at once, because that is just too flexible. But maybe you can run similar kind of arguments and talk about concordances where the singularities of the singular foliation are constrained to an extent. So you fix some control singularities and you try to work with that. And I think that's kind of quite interesting, actually. But OK, that's not a question. That's just, I find it nice. So OK, maybe yeah, that's the end. I don't know.
OK, thanks, Álvaro, for the nice talk. Questions?
Please, Mati. Oh.
Just a strange question,
Sure.
Because you mentioned the singular foliations that you look at are different from the ones of last
yeah,
week.
no, I see.
The ones of last week, they're also symplectic singular foliations.
They also had this? OK, I see.
I mean, there you can talk about symplectic singular foliations. Can you talk about symplectic singular foliations in your sense?
No, but I mean, OK. So in this last question, when I say singular foliation, I mean singular foliation, right?
In which sense?
In the sense from last week. So when I'm asking about, can we try to develop an interesting concordance theory for the singular foliations from last week, that's what I mean. And I'm not talking about transverse structures at all. I really mean just for foliations naked. Yeah.
Thanks for the nice talk. I remember something going on with these definitions of singular foliation with the closeness of the leaves. So in these Haefliger structures, the leaves are always close, no? But
in these Haefliger structures, the leaves are always closed.
Isn't it? No.
But I mean, you have like, right? I mean, you have like normal foliations as well, right? So they can. No, what do you mean by this?
Locally. I mean,
Locally,
because
sure.
locally
Yeah, okay,
are
sure,
the
sure.
fibers.
Yeah, that's what you mean. Yeah,
Okay.
then I agree. Yeah.
Well, anyway, I have two questions very quickly. Sure. But one, we were discussing about this already, but I was wondering whether if you can formulate this instead of using the classifying spaces, using the classifying stack.
So, okay, I mean, okay, as I told you kind of yesterday, but maybe it's good that to say. So, okay, the answer is I cannot, because I don't really know what a stack is. But maybe you can, and maybe we should talk about it, I think. Yeah.
Okay. No, but another question related to it is, even working with these classifying spaces, since you are going to show that certain map is Q connected. It seems, because of your proof, that it was rather homotopical. No?
For sure.
And
in fact, I should say that, I mean, almost all, I mean, all the statements I showed, all of them were, in some sense, kind of, you are phrasing them in classifying space terms, but all of them are proven geometrically on foliations themselves. One exception, though, is, for instance, in some sense, this intersection theory we are doing, it is kind of happening in classifying space, so to speak. Although you can also phrase it in the étale space and keep in, I mean, in some sense, maybe it's a stacky thing, so we are kind of maybe doing intersection theory in the étale space of solutions and kind of remembering how the gamma Q is acting. So maybe that's a bit of a, they're really, I mean, I would say that many of the classical arguments don't use classifying space so much sometimes, but this argument I do find that it does use this kind of more stacky thinking maybe. Yeah.
I see. But regarding the argument to show that or the arguments, the nature of the arguments, what about looking cohomologically? Because if you see that it is isomorphism,
so I should
in
say,
cohomology.
Right, so I should say that, I mean, what does theorem 2 really say, right? So, oh, there's a little hand moving there. Theorem 2, well, okay, I mean, what is the proof I showed you? What I showed you is that we are pairing against a point, right? So the point is, it's representing some sort of cohomology class, right? I'm pairing against something. So this is some sort of cohomology class, but I mean, it's not done in this like differentiable cohomology type of things. It's more like a geometric representative of the cohomology. So for instance, something I don't know is like, well, can you rephrase, for instance, this result using more other cohomology, more typical differentiable cohomology things and so on. And certainly, I mean, I think, for instance, that the argument by Thurston about how sharp this matter Thurston thing can go, right? So this Q plus 1, Q, 2Q plus 1, you cannot be as connected as that. I mean, I think that does use this kind of differentiable cohomology of Haefliger, but I don't know. Yeah.
My previous question,
Okay.
because it's really about the Haefliger structures,
Right.
and it goes in a direction complementary to what you have been doing.
Okay.
So the question is, you have regular foliations, and then Haefliger structures. You have symplectic regular foliations. Do you have symplectic Haefliger structures?
Oh, you mean, but you want to put them on the leaf? The symplectic.
Yes.
Ah,
That's what I'm saying. It's complementary.
Right. Yes, actually, that's a good question because it's a bit relevant to something I'm not saying. So, okay, let's see. Let's see if I'm able to explain this. So, when we're talking about this concordance, right, what we're saying is something like we're talking about things that are continuous into étale space. So, the étale topology is kind of key. However, if I want to be very fancy, and we do this quite often in these things, is that what you can do, you can do like a mix, right? So I can talk about, for instance, I can take Haefliger structures, but now instead of making them vary in the étale topology, which would be a concordance, I can make them vary in the Whitney topology. So you can kind of mix homotopies in the classical sense with homotopies in the étale sense. And when you do this, then, well, we are kind of doing something like this, right? Because we're just talking in some sense about foliations, where the symplectic structure is leafwise, so it's kind of some parametric thing, and it runs like this. So for instance, a statement that we could do is literally, well, literally the same. So you can construct, you can construct symplectic foliations, but the symplectic structure leafwise has one of these controlled wrinkle singularities. So yeah, I mean, but that's essentially the answer, right? So yeah, what we're saying kind of works parametrically for the usual notion of homotopy, and then that applies to the foliated case.
Yeah, sorry, I have a rather naive questions. I mean,
Oh, where are you? Okay, good, thanks.
in node theory, there is also of this notion of a concordance. And
Okay,
also,
say it again.
in the node theory,
In the what theorem? Not theory.
Not
Okay,
theory,
okay,
yeah,
okay,
there is
sorry.
also this notion of the concordance.
Right.
So I'm curious whether this story works in the hyperbolic geometry of this node complement.
Okay, so I really don't know anything about the hyperbolic geometry of knot complements, but I can tell you something about what we call concordance embeddings, which is what you are saying. So there's a general theory in H principle about exactly what you're saying. So you take a manifold, you can look at first, write at knots, so embeddings into the manifold. Now I thicken by interval, and I look indeed at kind of like embeddings of the manifold plus 1 into the manifold plus 1. Maybe I should write things because this makes no sense maybe. Right, so I mean, what you're saying, right, is I have a target manifold here, and I map from some other manifold, let's call it K for naught. And now what you can do is look at these concordance things, right? So this would be now you would map K times interval into M times interval, and this traces something, and you can study things like this. So this was, in fact, one of the big papers about this in the general case, not for knots, but for any manifolds, is due to Wood-Willey from the 80s. And, well, there's some sort of homotopy theory that is very H-principle in nature. So the answer in some sense is yes. There's a lot of work in H-principle ideas applied to this type of problem. They don't work very well in dimension 3, in fact, but they can be used to produce invariants of knots. I think it's related to this finite type invariance of Vasiliev. And well, that's an answer. And well, I'm interested in this, but it's somehow, I think that the techniques are kind of quite different, I would say. Yeah. Okay. I hope that helps. Yeah.
Can I have here, thanks Ecker. Two things. One
Please.
was, at some point you start using the word of generic geometry. Is that the precise?
The word what?
Generic geometry. Is that a precise term, or is just a...
No, that is the part that goes under in progress, yeah.
Okay.
I mean, so I'm thinking that, for instance, I mean, I don't even know how to do it precisely for metrics, right? So I would like to say something like, well, if I take a generic metric, I will have this property of isolation, and then I will be able to say maybe, oh, I cannot connect all the, I can construct many metrics that they are not concordant or something. That is what we would want to say. But we haven't thought about it much. That's kind of what's coming, I guess. Yeah.
And the other thing that it's kind of related is if you think, because we are in a Poisson conference, if you think about Poisson tensors, you could say, okay, if I look at constant co-rank Poisson tensors,
yes,
you are in a situation where you have a local model, and so your result that you described doesn't apply. On the other hand, if you take all Poisson tensors, you don't have any local model, but maybe you cannot say anything because it's just too. So
right.
Can you think of a class of Poisson structures that
I see. No, that would be nice. I agree. I mean, it goes a bit in the spirit of this singular foliation question, right? Also pinpoint kind of singularities that are interesting, not too flexible to get an interesting concordance theory. I think that would be very, very nice, in fact. Yeah. No, thanks, Reed. That's probably what one should do. Yes.
All right. Thank you.
No, thanks to you.
I don't see any further raised hands, so let's thank Álvaro again. And we resume at 11:30. Coffee break.